And if you thought the strong force was weird, now we're going to talk about the weak force. We can say a couple of normal things about the weak force. First of all, obviously it's very weak. That's something we can understand easily. And secondly, it's very short range. So again, particles have to be very close together to be able to exert weak forces on each other. Basically, we're talking side by side in the nucleus again. Okay, but whereas the force of gravity, the electromagnetic force, and the strong force are all things that allow particles to push another particle or pull another particle, the weak force, is it attractive? Is it repulsive? Is it neither? I don't actually know. We never talk about the weak force pulling or pushing. So here I'm going to remind you of this new phrase, an interaction. So a weak interaction is where particles exert weak forces on each other. Now, we've already talked about weak interactions, but what happens in them, as far as we know, is that particles, they don't push and pull each other, or they don't seem to. What they do is they change into other particles. So the weak force, for definite, changes particles into other particles. And this means that it is the force in action during nuclear decay, most nuclear decays. Okay, so we're going to be looking at those decays now, and we've done this already, but just to remind you that in a weak interaction, the total charge before has to equal the total charge after. Same for baryon number and same for lepton number. And with that in mind, however strange this might all be, we can actually do some stuff and get somewhere. Right, there are 3 weak interactions that you want to memorize or be able to work out very, very quickly. And the first is the familiar beta decay. So this is where a neutron in the nucleus decays into a proton, an electron, and another particle I haven't filled in yet, and these two are chucked out the nucleus. So when they were first learning about this, what they observed was a nucleus that turned into a different nucleus, and an electron came out at high speed. Right, so we're going to use our conservation rules to work out what that particle is. So charge, first of all, that's the number at the bottom. So 0 before, 1 minus 1, so this one must have no charge. And then baryon number, that's the one at the top, so 1 before, 1, 0, that needs to be a 0 as well. And then lepton number, no leptons before, not a lepton, yes a lepton, so this needs to be an antilepton. Right, the leptons that have no charge and no mass are the neutrinos, but it needs to be an antineutrino. And remember, we match the type there. Right, so while this all might be very strange, we've used our conservation laws and we've worked out what the particle is. We can work out what a weak interaction involves. Next up, we've got positron decay or beta plus decay, and that's where a proton in the nucleus turns into a neutron, which stays in the nucleus, plus a positron, which comes flying out, and another particle that comes flying out. Here we go again. Charge, we've got 1 there, so this is 0. Baryon number, 1 there, so this is 0. And lepton number, none there, none, minus 1, so this needs to be 1. So this now needs to be a lepton instead, and that means it's a neutrino. And then one more. The third one you need to know is electron capture, and this is where an electron actually gets close enough to a proton to interact with it. And then what you have is the proton from the nucleus plus the electron that's come too close to the nucleus, and they interact and turn into a neutron and an unknown particle. So here we go once again. 1 minus 1 is 0, so 0. I mean, I think you can probably guess what it's going to be. Baryon number 1, 1. Lepton number 1, and so this needs to be a lepton. And that makes it another neutrino. Okay, and just before we leave this, I'm going to just look at positron decay again as an example, because in fact, when we say that the proton turns into the neutron, actually it's only one of the quarks that's changing, and that's true for all of these. It's only one quark that's changing. So if we just do positron decay again, this is what's actually happening. The proton, remember, is up, up, down, and the neutron is up, down, down. So it's just the one up turning into a down there, and then everything else obviously has to be the same. So just confirming that this is going to make no difference to how we go about things. Remember the charge at the bottom, so we're going to put 2/3 down there. And what are we going to put for the baryon number? Well, we're going to say that the quark is 1/3 of a baryon, and then everything will work just as before. So a d quark, down quark, that's minus 1/3 there. Okay, and so we can see charge 2/3 before, 2/3 total after. Baryon number 1/3 before, 1/3 total after. And lepton number none before, and then after none, -1, 1. So it all still works. And when you've got one particle turning into others, we're referring to that as a decay there. We're saying we're ending up in a less energetic state there. So these are all referred to as decays. Okay, so here is an example question. Have a go at that one. So I'm going to start putting in my charges, and straight away here I can see the charge before is 2/3, and then after it's, put my zeros in there, after it's -1 1/3, so it's definitely not that one, and this one is going to have the same problem, so not that one either. So now these two, we can see they've been quite sneaky, because charge conservation works out in both of them, -1/3 before and a total of -1/3 after. And then, so then if we do baryon conservation, we've got all the quarks are 1/3 and all the leptons are 0. So again, baryon conservation number works out. So it's going to be lepton number that decides it. So on C, we've got no, hang on, switch back on the pen. On C, we've got no leptons before, and then that's none. That is 1. And that is also 1. So that's wrong. We've got 0 leptons before and we've got 2 after. So C is also wrong. We need to have an anti-neutrino at the end there. So it's D.